Let's do some problems of regarding operators. First, we will deal with Hermitian operators. My problem is the statement of the problem is like that. We need to show that the following two definition of Hermitian operators are equivalent, and the definitions are equation number 1 and equation number 2. Equation number 1 is this: Q is an operator sandwiched between kth and bridge, and this is equal to like this. So if in case of Hermitian operator, if Q is an Hermitian operator, we could write like this. Instead of writing this kt, using this vertical sign, I can also write it like this, like kth and then directly qh. This is an alternate way to write the expectation value. This is my equation 1 and this is equation 2. Now these h, f, g, these are actually functions in Hilbert space that is given to me. Now I am starting with equation 1, that is the first definition of Hermitian operator. I am starting with this. Let me tell you something, that as we are in vector space, because Hilbert space is a vector space, so linear combinations of two functions within the space lie within the same vector space. That means if I make a linear combination of f and g, these two functions, then their linear combination will give me hx, which lies on the same Hilbert vector space. And this is another linear combination of f and g, and this gives me h tilde, because this is fx plus igx, and this is equation 3. Now I am using this first linear combination, which is fx plus gx equal to hx, in my equation 1. Equation 1 is this: h bra qh equal to qh and then h ket. Now in place of h, I am writing f plus g. This linear combination is written here in place of h, and in the left hand side also it is qh then ket h. So in place of h, I am writing f plus g, so is here. Now doing some simple algebra, I got 4 terms in left hand side. My left hand side now looks like fqf plus fqg plus gqf plus gqg, and right hand side similarly I have 4 terms. This is qff plus qfg, and then it's qgf plus qgg. I have already taken equation 1 correct. So this fqf must be equal to qff, so I can cancel qff, that is the first term in right hand side, with the first term in the left hand side, and similarly the fourth term in the left hand side, qg, and then this is bra g, this is going to be cancelled out with the fourth term in the right hand side, which is qgg. So we cancel 4 terms, this with this, and this, I'm sorry, there is a focusing problem. So I am cancelling this with this, and this fourth term with the fourth term, and I am left with 2 terms in the left hand side, 2 terms in the right hand side. This is my equation 4. Now we are using the other combination, which is h tilde equal to f plus ig. In place of h, now I am writing h tilde for equation 1, and in place of h tilde I am just writing the linear combination of f and g like this. And just as I have done before. I am doing some algebra, splitting up these expectation values, cancelling similar terms, like in the left hand side FQF is getting cancelled with QFF, and in the left hand side IG QIG will be cancelled because of the fourth term in the right hand side, which is QIG IG. And I got equation 5, which contains two terms in the left hand side, two terms in the right hand side. Let's use the property of expectation values. This is expectation value written in Dirac notation. This is Bra and Kate notation. C is a constant. And in terms of integration, I can write the expectation value like this. As C is constant, the integration will only be done for f star x and gx. And in terms of Dirac notation, this integration can be written as the scalar product of f and g. This is my equation 6. Now I am using another property of integration expectation value. This is also I am exploiting just the properties of expectation values. So here, as C is in the Bra side, so this could be written like this. When is an integration symbol. So this can be written as C star fx and gx dx. C star is a constant. This is just a complex of C. So C star can be taken outside. I am left within the integration with f star x and gx, which can be written in Dirac notation like scalar product of fg with C star outside. This is my equation 7. So what we get is equation 8. These two are very important. Like when the constant is written in the ket, I get C and then the scalar product of the two functions. But when C is written here, that is in the Bra notation, Bra vector, so we get C star and then the scalar product of fg. This is my equation 8. And I am using the equation 8 in equation 5. My equation 5 looks like this, which was fqig plus igqf and equal to qfig plus qigf. As this I is in the ket vector, so recalling this would be plus C and then just the number itself C and then the scalar product of fg. So if I is taken outside, I will get only plus I, then the expectation value of expectation value of q within the two states f and g. But here the I is written in the Bra vector like this. So if I take I outside, it would be I star if I follow this definition. So this is minus I, there is the complex conjugate of I itself. So for this second term, I will get minus I GQF. And the same procedure is applied here also. Dividing both sides with I am getting equation 9. Now equation 4, which was like this, and I have obtained equation 9. I am adding equation 9 and 10. So this second term will be cancelling out and the fourth terms are also getting cancelled out. So I am left with this. This is my equation 2. So starting with definition 1 or equation 1, I have arrived at equation 2, which is the second definition of a Hermitian operator.